Hi everyone, my name is Melissa and I'm a graduate student in the Chemical and Biological Engineering department. And today I will tell you about my quest for the ideal catalyst. So let's imagine that you have a big party coming up. Maybe it's a birthday celebration, or maybe it's a goodbye party, or maybe your parents are visiting. The case is that you don't have anything to wear, so you go to a clothing store. And the first thing that you do when you walk into the clothing store is you screen the entire place with your eyes. And immediately you find the clearance section, because you're a graduate student that doesn't get paid a lot, so you have to save some money. So let's say that you're a size small. So you you look through the things that are labeled size small. You quickly find something you like, you try it on, and then you buy it and then you leave. But instead, let's pretend that you walk into a messy store. Everything is a mess. Women's section and men's sections are all mixed. There are no labels on anything, so you can't tell the difference between extra small and small. So now you have to spend a lot of time trying on different things until you finally find something that actually fits. In the same way, scientists are trying to find different ways that we can convert natural gas into useful chemicals. Now, as I'm sure a lot of us in this room know, natural gas production is escalating. And so there is a lot of interest in trying to find ways that we can use natural gas as a resource for making the commodity chemicals that are used for making things such as the fuels that we use to drive our cars, the plastics that go into the water bottles and the containers that we use, and the fibers and textiles that are used to make the clothes that we wear every day. And as opposed to an organized store where, these transformations in industry don't happen magically. They're usually possible through the use of materials called catalysts. And as opposed to an organized store where things are labeled, there are no clear labels for what a good or a bad catalyst might be. And so scientists are spending a lot of their time trying to find catalysts that they think might be good for a reaction that is important for natural gas conversion. And so this is where my research comes in. And before I go into the details of my research, let me first tell you what a catalyst is. Now, let's imagine that we have to get to the other side of this mountain. And in order to do that, we have to climb up the hill. And by the time that we're on to the other side of the mountain, we're tired, it's weeks and days later, and so it took us a lot of work to get there. But instead, let's pretend that we found a tunnel. And let's say that we had a car. We can get into the car, drive through the tunnel, and get to the other side in just hours, with a lot less work and a lot faster. A catalyst does something similar for chemical reactions. If we had the chemical reaction A plus B going to P, like most chemical reactions, this one has an energy barrier that it has to overcome in order to form the products. It's like the hill that we had to climb in order to get to the other side of the mountain. And just like the car that we had to drive through the tunnel, a catalyst finds a new pathway a new and easier pathway that the reactants can take in order to get to the products. But at the molecular level, how does this happen? In industry, what we have are called heterogeneous catalysts. And these catalysts provide a surface for reactants to come together and react. However, some of the disadvantages of these catalysts is that the sites that the reactants bind to are not very well defined. And what I mean by this is that the sites are all different, and they can lead to undesirable products. It's like choosing the wrong car to drive through the tunnel. It can get us to the other side of the mountain, but at the same time, it's releasing carbon dioxide and greenhouse gas emissions that are bad for the environment. And so in order to avoid all of these bad side products, we have to make a catalyst that has identical and well-defined sites that will only go through the reactions that we want them to. And so in my lab, we study materials called metal organic frameworks. And inside the pores of these materials, we can grow cluster catalysts by depositing one metal atom at a time. And in this way, we can grow identical sites that will only make the products that we want them to. But if we look at the periodic table, there are a lot of possible catalysts that we can make. Let's say that we only look at the metals that are usually studied for catalysis. And if we just want to deposit 2 metals, we're already over 500 cluster catalysts that we can make. Imagine having to design and test each one of these. And what if we wanted to extend through the periodic table and maybe deposit 3 or 4 metal atoms? It would take us a lot of time to go through all of these catalysts. And so what we need are descriptors or labels that can tell us how good a catalyst is for a particular reaction. So like I mentioned before, a catalyst finds a new pathway that reactants can take in order to form the products. Computationally, we can find what these energy pathways are and find what the energy barriers are that can give us some indication of how good a catalyst is. But even with computers, this can take us a very long time. And so what we can do instead is take a sample of catalysts and develop relationships between a descriptor that we choose. It could be the interaction energy of the reactant with the catalyst and the energy barriers. And once we have this relationship, we can use this to predict the energy barriers for a new catalyst, and that way predict how good this catalyst is for a reaction. And so in the end, we end up with a visual plot that can allow us to screen for a large number of catalysts. And just using the descriptors, the interaction energies of the reactants with the catalyst as the descriptors, we can make this visual plot and identify the region that contains the best catalyst. In this case, in this example, this red region right here. And then we can take this, go to the experimentalists, and tell them, these are the catalysts that you should be trying to test and design because we find that they can be very good for the reaction that you're interested in. And so in conclusion, we use chemistry and computers to guide experimentalists through the discovery of better catalysts for natural gas conversion. Thank you.